Welcome back. In this video, I will be covering part B of concepts in section 14.6. So in the earlier part A of this concept 14.6 video, we saw the definition of directional derivative. And now we are going to define the gradient vector in this part, and then we are also going to see the geometric significance of the gradient vector. Define the gradient vector del f, you pronounce it as del f, for a function f of 2 or 3 variables. If f is a function of 2 variables, then del f of xy, the vector, so use the vector notation there, del f of xy is f sub x, partial derivative of f with respect to x of xy, comma partial derivative of f with respect to y of x at x comma y, which in short can be written as dou f over dou x, or partial derivative of f with respect to xi plus partial derivative of f with respect to yj. That is a gradient vector. For a function f of 3 variables, del f of xyz is fx, fy, fz. These are the xyz components of del f. The partial derivative of f with respect to x, I, plus partial derivative of f with respect to y of j, plus partial derivative of f with respect to z of k. Express duf in terms of del f, where u is a unit vector a comma b. So we can write du of f of xy, u is a vector by the way, u is a unit vector, du f of xy can be written as del f, the gradient vector x comma y at xy dot the unit vector u. For the 3-dimension, du of f of xy is a gradient vector del f at xyz dot unit vector u. So if you notice here, earlier when we derived du, when we said what the formula was, du is fx a plus fy b. So that is the definition. So if you consider del f dot u, if we're taking 2-dimension, for example, it is fx comma fy dot a comma b. So the dot product is the multiplying the corresponding component. So fxa times fyb, that's exactly what we defined in this part. So another way of writing the directional derivative du at f as a dot product of the gradient vector dot the unit vector u. So please refer to the problems based on the directional derivative in the section videos. So problem number 11 and 19 are done in those section videos. Please refer to them. Explain the geometric significance of the gradient vector. The gradient vector of f gives the direction of the maximum increase of f maximum increase of f. The gradient vector of f, which is a vector, del f, gives the direction of the maximum increase of f. It always points in the direction of the steepest ascent or the maximum rate of maximum increase. On the graph of z equal to f of xy, del f or the gradient f points in the direction of steepest ascent. Also, the gradient vector is perpendicular to the level curve. Always the gradient vector is perpendicular to the level curves or level surfaces of the function. Next theorem, suppose f is differentiable function of two or three variables. The maximum value of the directional derivative du of f of x is length of del f x, which is the magnitude of the gradient vector is the maximum rate of change. And it occurs when u has the same direction as the gradient vector del f of x. When the unit vector and the gradient vector are parallel to each other, then the maximum value of the directional derivative is length of the gradient vector. Problem number 23 is based on the directional derivative and the gradient vector, and it's something to do with the maximum rate of change. Now, problem number 23 is done in the section video. Please refer to the section video for problem number 23. So in addition to those problems that I mentioned, problem number 31, the word problem is also done in the section video. Please refer to these. So you will see these problems, number 31, 23, 19, 11, all these problems. Number 4, all these are done in the section videos. Please refer to them. Hope this video helps.